This, as George introduced, this is what's new in digital predistortion. This is a talk I've given for about 3 years as a distinguished microwave lecturer. And it has changed a little bit over the years, and we'll see where and why that is as we progress. So, okay, what's new in digital predistortion? I thought I'd really ought to start with what's old in digital predistortion, so at least we're all on the same page and you can see where we're going. So we'll start with that, a little bit of a recap on what DPD is, and then some areas where we're going to improve. And what's new in DPD, the sort of challenges that I see are really bandwidth. We're now seeing multi-protocol signals, multi-band signals, and that's really quite challenging, not just for the predistortion, but for the PA design and the whole transmitter. Increased bandwidth also means challenges for sample rate, the digital sample rate of the system, and how we manage and handle memory effects. And the third new challenge in DPD is bandwidth. And what DPD methods can we apply for high-speed implementations, real-time coefficient adaptation for rapid changes in the signal quality and signal strength and things like this. So I'll be addressing bandwidth, basically, in this presentation. So, okay, what's old in DPD? What does a digital predistorter do? Well, in a typical PA or transmitter system, the power amplifier is the main source of distortion, and that really affects the quality of the signal that you as a customer will receive on your cell phone. So the idea of a predistorter is we take a nonlinear function, which is the PA distortion, we put in front of that another nonlinear function, and the product of these two nonlinear functions, by some sort of magic, turns out to be a linear result. So the output for the PA is simply a scaled version of the input, which is what we'd really like. Features of the predistorter. Sorry, this is quite hard from here. The typical PA tends to have a compressive characteristic, so eventually it'll compress as the signal level increases, and it'll finally get to a point where it saturates and you get no more power out. So to get a linear response, the red line, the predistorter's got to expand the gain. So one of the things that the predistorter does is increase the signal level going into the PA to overcome the compression. Of course, it can only do that up to the maximum power. You don't get any more power out than the original PA. Another way of looking at this is in the frequency domain. And the action of the predistorter is we have this nice clean signal going in, and we want to get a nice clean signal coming out, but the PA is going to add a whole bunch of intermodulation distortion around the signal. So the job of the predistorter is to add some distortion, add some intermodulation distortion in such a way that the combination of the distortion from this guy and the real signal, once that's all distorted by the PA, is a nice linear signal. And that's what we're trying to do, and it's an exercise in essentially nonlinear mathematics to get that to work. And so that's really what predistortion is. Practical system is a little bit more complicated. We have a whole range of things. The PA you probably recognise. There's the RF domain, which is taking the digital signal through some data converters, up-converting, amplifying. And the way the predistorter works is to take some of the signal, sniff some signal from the PA, down-convert that back to the digital domain, and then compare what we're seeing at the output with the input signal, and making some adjustments to the input signal in order for the two signals to be clean and linear. So the output is a replica of the input. A whole range of other things that I'm really not going to talk about today. I don't really have time. Traditional DPD systems, these have been going for about 20 years or so, tend to use things like lookup tables. or nonlinear filters to generate the nonlinear response. You can have a lookup table that models the gain expansion so that for any input power you'll simply read a higher version of the input power to the PA to compensate for the compression. And this can be done in FPGAs or application-specific ICs. Up until very recently, the sort of bandwidths that you would see published for predistorters were in the sort of 5 to 10 megahertz range. Single channel wideband CDMA typically is something that people would be doing, say, 4 or 5 years ago. It'd be simple modulation, possibly multi-carrier. You know, 2-carrier wideband CDMA was seen as a challenge about 5 years ago. Multi-carrier GSM is still a challenge, so we'll probably not talk about that again today. And the coefficient adaptation, as you see, it's a feedback system. The coefficient adaptation was relatively slow, done on a separate floating point DSP chip, and we'll look at the architecture in a little bit. And so this may take several seconds to adapt, and then you'd be modifying that as the signal levels changed. And everything was pretty relaxed, really. So here's just how a lookup table sort of appears. The PA gain compresses, the predistorted gain expands, so you detect the power at a certain input level. You know what the PA power is going to be. It's going to be compressed, so you read off something from the predistorter just to increase the input. And that's sort of fairly good at correcting simple PA systems. You'll hear a little bit later memory effects, and I've got some interesting things to say about memory effects. But memory effects, you need to look at the past history of the signal, and we'll talk about that. And generally, you just end up with a layer of lookup tables to do that, so it becomes a little bit more complicated, but it's not terribly difficult. So that's where we are. Where are we going to go? As I say, these are the challenges. What's new in digital predistortion? We've got a challenge of increased bandwidth in the signals that we have to handle. Typical multi-protocol signals, instead of just having 1 or 2 carrier wideband CDMA, we'll have LTE and wideband CDMA and maybe 4 or 8 channels of this, so this is now getting actually quite wideband signal. LTE and multi-carrier GSM. I've written up to 8 carriers here. That was pretty challenging 3 years ago. 1 or 2 of the tier 1s are now looking at anything up to 12 or 16 carriers, as well as a bunch of LTE carriers. And we're all wishing multi-carrier GSM would go away fairly soon, because it'd make our life a lot easier. Wide bandwidth, 40 to 60 megahertz occupied bandwidth in a 100 megahertz total is generally a request that you get nowadays for the DPD systems that we have to build. We're also seeing multi-band operation, and this is something that's built into the current LTE release, and gets even more difficult with future LTE releases. That to get the amount of data that you need into the available bandwidth, the service provider may want to put signals at, say, 2.1 gigahertz and 700 megahertz, and use that as just one continuous band. That's more of an overall system problem. You have 2 transmit bands, and that's something that's a bit more difficult to deal with. Generally this means 2 PAs, so from a DPD point of view, it's not quite so challenging. But getting up to these sort of bandwidths, we end up using much higher sample rates than you really want to deal with. 250 to 500 megasamples a second is now pretty typical, and you need this oversampling because what you're trying to do is not capture only the signal of interest, but all of its intermod products up to, say, 5th order or something like that. And so you'll see, 100 megahertz of bandwidth. We'll need 500 megahertz of DPD bandwidth to capture. Crest factor reduction. I said I wasn't going to mention that, but here it is on the slide, which is a pity. Okay, the crest factor reduction can be challenging. This is actually a very math-intensive exercise. The point about crest factor reduction is that since DPD is an expansive function, makes the PA work harder, if you can reduce the crest a little bit beforehand, before you do the DPD expansion, then you don't get as much gain expansion, and you cannot stress the PA quite so much. So, but this can be challenging as you increase the bandwidth. Signals across 2 bands. It's incredibly difficult to do a good crest factor reduction job on that. It's really quite challenging. What do I mean by wideband multi-protocol signals? So when I started as DML about 3 years ago, this was the challenging signal. This is the Sprint signal. Sprint, through no fault of their own really, ended up owning bits of spectrum at each end of band 2. This is 1900 megahertz. So they owned a bit down here at 1930 and another bit up here at 1990. They'd had this for a while, so they're putting regular narrowband CDMA down here, and then they wanted to use LTE up here. And of course, they're as cheap as anybody else, so they just wanted to use one PA for all of this. So the PA had to handle 65 megs. It's not only got to manage the adjacent channel leakage around each of these, but also manage the intermodulation between this clump of energy and this clump of energy. And that's quite important for this particular signal, since the receive band for band 2 happens to be just about 60 megs down here, which is a real problem. And so you end up, if you don't kill the IM3 product that appears here, you'll simply saturate your receiver and screw everybody up. So that was actually an interesting challenge about 3 years ago. I think it's been pretty well solved by now. As I mentioned, LTE, certainly release 10 and subsequent releases have a lot of interesting things going on. Release 10, which is, I think, the currently deployed one, allows for up to 5 carriers contiguously in any band to accommodate the amount of data that you may want to transmit. So the worst case would be a 20 megahertz carrier, so this is where the magic, very often quoted figure of 100 megahertz bandwidth comes from. So this is in intraband contiguous spectrum allocation. Not many bands are 100 megahertz wide, but band 7 up at 2.6 gigahertz, that's about 70 megahertz wide. But for time domain LTE, there's a number of bands where this actually applies. For reasons that may not be obvious, this is actually possibly a bit more difficult than this. This isn't supported in release 10, but is in release 11 and subsequent releases of LTE. And so the same 100 megahertz band, but dropping a couple of the carriers out, so transmitting here and here. You've got to be very careful about the distortion that appears in this band, because other customers or the users of that band are going to get really annoyed with you if you start putting energy in here. So pre-distortion of this to keep your intermodulation energy down in this region is really quite hard. And this was the interband non-contiguous that I was talking about. This could be one band here and one band here, but this is treated as one contiguous band of energy as far as the signal baseband is concerned. That's more of a signal management issue. I don't think it's, provided you have a different PA for each of these, it's not really a problem as far as DPD is concerned. But if and when these clever PA guys get to designing PAs that are very, very wide band and you can accommodate disparate frequency bands with one PA, then you're going to have to linearize that one PA with some predistortor, and that becomes a real challenge. That's really hard. And that's this sort of thing. Multi-band signals, yeah, we're now getting asked for these. This is a real challenge. It obviously includes multi-protocol. It's really downlink only. And examples include, band 1 plus band 2 or band 3, and this example is band 3, the old GSM band, and band 1, which is wideband CDMA, and this is now being refarmed for LTE, and LTE is appearing with possibly multi-carrier GSM in here. And people think it would be really nice if you could do this with one PA. So accommodating the bandwidth expansion of each of these bands here to accommodate their adjacent channel energy. Let's assume then reasonably well behaved and there's no overlap here. That's a real mess. Then you're looking at 600 plus megahertz of bandwidth for your DPD system. That's a real challenge. It's a challenge for the data converters, it's a challenge for the digital system, and not least a challenge for the PA design. If that's not bad enough, we're also getting asked this, band 1, 3 and the band 7 for frequency domain LTE. Again, there might be multi-protocol in these. This is an LTE band, but now you're talking double the bandwidth to accommodate these. And then, of course, you've got the intermod products between this clump and this clump of energy dropping more signals around here. And who knows what's in here? Some other users are around that part. So this is a real challenge. You know, if 600 megahertz was hard, this is more than twice as hard, believe me. So that this is actually quite difficult. So how might you do that? You might want to simplify your transmitter, software-defined DPD. Place all the demands now on your data converters. So you're needing data converters here and here that can accommodate gigahertz of instantaneous bandwidth at maybe 2 gigahertz center frequency, and a wideband PA. So essentially, we've removed a lot of the RF system here. Which is bad news for the MTTS guys, but possibly good news for these IC designers. And so challenges here, challenges in the algorithms and challenges in these data converters, but could be quite a disruptive architecture if you could apply it. Okay, so that's the problem of increasing signal bandwidth because people like you and I want to stream video down our phones at any time of day or night, and so the bandwidth demands are just ever increasing. If you increase the bandwidth then to accommodate that amount of signal instantaneously, you're going to end up clocking the system, the digital system, much faster. So that's one aspect. The wide bandwidth will also give rise to some memory effects. You know, frequency domain, frequency response effects are one of them, and others are due to a whole range of maybe thermal effects and other charge storage effects in the system. I think we're doing okay. So we've already sort of mentioned this. The wide signal bandwidth, as we saw, the DPD rule of thumb is maybe 3 to 5 times signal bandwidth to accommodate the IM and adjacent channel products. That tells us, 100 megahertz signal bandwidth requires a 500 megahertz DPD bandwidth, so very high sample rate of the DPD system. So we've seen that in terms of the RF bandwidth in the previous few slides. From the point of view of things like the data converters, when I started this presentation, the state of the art in the D2As on the transmit path was maybe a gigasample per second at 16 bits, and that's pretty much state of the art, what people would do. The ADCs for the DPD receiver were probably around 500 megasamples a second. Maybe that's actually pushing it, and maybe 12 bits. Now I'm retiring. What we have is pretty much state of the art 6 gigasample per second DACs, and with well over a gigahertz of instantaneous bandwidth are on the market nowadays at 16 bits. So this allows that software-defined radio approach, and released, just in the last year, a rash of ADCs at 12 to 14 bits that are clocking at 2 to 3 gigasamples a second, and will accommodate conversion not only in the first nyquist but the second. So you can actually be doing nice captures at 2.1, 2.4, 2.7 gigahertz, and again with wide bandwidths, maybe 600 megahertz bandwidth. So we're getting to the point of software-defined DPD systems. There are these sort of sample rates means that you're going to have very large oversample rates for the various signals. So back in the digital system, there's a lot of filters and interpolation that can introduce errors. So these are digital system challenges that are perhaps not of great interest to you, but they're also, depending on the architecture, potential image rejection problems that you need to deal with. So that's one aspect of how the wide signal bandwidth affects the digital system. Another way is memory effects. Now, I mentioned these earlier, and I said I would talk a little bit more about memory effects. So this is the slide. Here's our input signal. Here's our nice, clean replica output signal from the PA. And it turns out that the output signal at any instant in time from the PA is dependent not only on the input at that time, but on some past history of inputs, some number of some amount of time previous to that will affect what the output is. And an example of that might be if the input signal suddenly or has been at high power for a long time and then drops in power. While it was at high power, the PA, not being 100% efficient, will warm up. Its gain is going to change a little bit, and so the gain will be a little bit lower because of the heat than you might normally expect just from this this instant of input power. So things like that will affect the way that the PA behaves, and you've got to accommodate some history. And in fact, Boyd and Chua showed about 15 years ago that having a finite memory is essential for being able to build behavioral models and DPD systems. Otherwise, you'd have to build one that operates for infinite time just to be able to get the right answer. So fading memory is not only essential, but actually an advantage for being able to build models and DPD systems. So what does that actually mean? We need some finite history beyond which you can tend to forget it. You know, if it's a long time ago, then you can really forget what's happening. So there's some finite memory time that is required, apparently. So let's say we've built a system and it's running at 100 megasamples a second, and so we need whatever it is, 5 samples or something of memory to describe the PA properly, so we can build a DPD system. Let's now increase the bandwidth, so we increase the clock rate, so we've got more samples. So now, does that mean, now we're sampling much more quickly, does that mean we need to capture twice as much history in terms of digital data than we did beforehand? And I suppose if you think of memory as a finite amount of time where things happen, that is probably the case. I have a perspective on this that is probably not universally accepted, but here it is anyway. Is it memory or is it dynamics, and do these two things mean the same thing? Do these two words mean the same thing? Here's very, very simple and obviously not complete piece of work. I started off with a 2-carrier wideband CDMA signal, and this was at 60 megasamples a second. The funny number is because of the chip rate of wideband CDMA. And I built a model, a Volterra-based model, heavily math model, and I required memory delays, 0, which is the instantaneous signal, 1 sample delay, 2 sample delays, 3 sample delays, and I get this model, and it's got a good normalized mean square error, minus 40 dBs or something. So it's actually quite a nice model. So okay, I can now model a PA that will handle a 2-carrier wideband CDMA signal. What happens if I now apply an 8-carrier wideband CDMA signal? It's been sampled at 4 times the rate, 250-ish megasamples a second compared to 60. Can I use that same model without any change at all and get a reasonable answer? Well, that's the green curve, and yeah, you've seen the right sort of expansion. The power is correct, and I did nothing else except scale the signals to the right right levels. So it's a credible model. Might not be absolutely accurate, but it's a reasonably credible model. Whereas if you say, I need the same memory, so it's just sampling at the same 1, 2, and 3 samples. You could then argue, but this, because I'm sampling a lot faster, I'm not getting the same memory depth. So if I now take the same model, but take the memory delays instantaneous, the same, but now take the 4th, 8th, and 12th samples, which correspond to the 1st, 2nd, and 3rd samples at this clock rate, will that give me a good model? And the answer is, well, not really, because that's the red curve. So that you can't do. So not conclusive, but just something to think about. And one of the reasons that I sort of brought this up is I used to do, I told Paul I wasn't going to do behavioral modeling in this lecture, but here's a mention. I used to do behavioral modeling doing time series analysis, and originally we did that using derivatives, and we found we could build great models of wideband ICs with second time derivatives. And we then thought, well, derivatives are quite hard to do in a digital system, so let's just use delays. And we found that we could build a system that wasn't too bad with a couple of delays. And actually, if we ended up using delays, and since you knew the signal all the time, you can do acausal things. So if we had delays of +2, +1, 0, -1, and -2, so in other words, a nice curve around the sample that you want, essentially you're building a second derivative quite carefully of that signal. And so is it a derivative you're after, or is it just a bunch of delays to get something called memory? Memory is just energy storage and nicely described by continuous time signals. So I think all I'm doing here is building a good derivative. And you can argue that later, okay? The sample rate effect, bandwidth, clock sample rate, the number of multiply and accumulate calculations that you need to do to calculate DPD. The higher the required bandwidth, we've seen the higher the sample rate that we need, so that's the higher the digital system clock, and that means you're going to have to do lots more arithmetic calculations, and so greater DSP processor power is required. So lots more cost is being built into this, more power is being consumed, possibly more memory terms are being required, and more RAM is needed for waveform capture and coefficient storage. So just increasing the bandwidth increases the cost and power consumption and complexity of your digital system that is, one might argue, the heart of your DPD system. So just taking a reasonable polynomial calculation of a predistortor, doing a nonlinear model with a polynomial and some Volterra cross terms. 11th degree polynomials are not uncommon in DPD, it turns out. These are hard to get convergent, but people use them, including me. The cross terms, we'll talk about these in a little bit more time. So these are the memory terms, and you can get a nice multiplication of different delays to describe the dynamics. So 10 multiply and accumulates and 3 shifts here, maybe 60 to 80 multiply and accumulates, depending how many, on the complexity of the terms that you use. Typical data sample rate, about 370 megasamples a second, is pretty standard nowadays. And if you work out that sample rate and these number of multiply and accumulates, then the processing you require is 30 complex giga multiply and accumulates, or about 200 giga ops per second, real operations per second. Now that's pretty hard. So the power consumption of that, and these are figures that I got from Department of Energy's exascale grand challenges, 28 nanometer CMOS. These are quite conservative calculation numbers, but it means you're still going to be burning about 3/4 of a watt for your DPD. Not much in the context of a base station PA that's chuffing out 200, 300, 400 watts, but you can't use this in a handset or you know, a 1 watt femtocell and still look competitive in the market. So you might need to do something else. So that's a challenge. How do you keep the power down? Can you reduce the sample rate? Unfortunately, it's not possible on the forward path, on the DPD path, because you've got to include all the nonlinear contributions at every single sample. But you can do it on the observation path if you're careful about the architecture that you use. You could also argue that maybe you don't calculate the polynomial at every time and you use a rather more sophisticated lookup table approach, and that there is that too. So those are the digital challenges of bandwidth. We've had the frequency domain aspects of wide bandwidth, the digital aspects of wide bandwidth, and now you might say more digital, but the more algorithmic aspects of what wide bandwidth introduces for you. So I'll start off with just by describing a couple of the architectures for DPD systems in terms of how they tend to work. So this is a more sophisticated version of the picture I showed on the second slide. You know, you have your digital predistortion system. It goes from the digital domain to the RF domain. So this is all the data converter stuff. There's the PA. We sniff the output of the PA, convert back to digital, and in this particular architecture called indirect learning, we do a post-distortion, digital post-distortion if you like, which you might say is building a model of the PA. And so you compare the post-distortion signal with the pre-distortion signal, suitably delayed so they align properly. So if your DPD is working, then the output from your PA is linear, so it's the same as the input here, and so the pre-distorted and post-distorted outputs should also be the same. And so you've now got a converged system and everything's okay. So this is known as indirect learning. It's very popular in the academic circles. Almost every paper you see published on DPD will have, 90% will have indirect learning. And I think that's because it's really easy to set up the cost function in the update, and the coefficients seem to fall out fairly naturally. It does have a number of problems. It does have, if you work through the math, it has both an additive and multiplicative bias built into this, so strictly speaking, you can never get the right answer. But as I say, still popular and works well enough. I mean, the point is you're not trying to get the right answer, you're trying to get an answer that's good enough to meet the spec. So this is one technique. You can't use subsampling in the down conversion path because you're comparing the two pre-distorted signals, and you know this is running at full rate all the time. An alternative, which is a much I'll put everything on. There we. Oops. A few bullets missed there for some reason. Sorry about that. This is you might say, just an adaptive control problem. Now you've got the input signal. You're comparing the output signal directly with the input signal. It's a classical control system. And you've got your predistorter and PA. And so if your predistorter is working, your output signal is a linear replica of your input, and you're converged. And so it's a fairly natural thing to do. This doesn't have any bias. It's a much easier system to put together. And no, I can't read what's disappeared from there. But you do have the opportunity here, because although this will be running at full rate, you can downsample here and downsample here, so your estimator can run at a much slower rate and be a lot easier to calculate. Doesn't have any bias, so is, like any feedback system, more likely to converge to the right answer. But unusually, for some reason, doesn't seem to be as popular in the literature as the previous example. So what sort of functions does a predistorter consist of? Well, a very popular technique, again, quite old, memory polynomial, which take your input signal, multiply, put it through a polynomial, so you get all the nonlinear products. Here are some delays for the memory terms, and again, you get nonlinear products. You add them all together, and you end up with actually a fairly straightforward polynomial equation of your output signal as a function of the input. And so this is actually very popular. It's been used for a long time. Classic papers in predistortion use this technique. And it's great for relatively narrowband signals, but the memory effects are pretty, which these delay things here, are pretty rudimentary. And a more general purpose nonlinear dynamic model is the Volterra series and modifications of that. And you can see now, instead of these products being all of the same delay, you can get delay M1, delay M2 can be different. You get these are the cross terms. And so if your memory is of any reasonable number and your polynomial is of any reasonable size, you can get thousands and thousands and thousands of coefficients here. And that, again, is pretty well impossible to calculate as the math is just virtually impossible to do correctly. What does it mean in terms of practice? And just mapping this onto the memory polynomial structure where you have the polynomials and their delays, you're now getting cross products between all these, and that's where you can see the number of terms increases dramatically. And so some pruning of these cross products and these terms is essential, and there's an awful lot of work gone on in the last 5 years in terms of systematic ways of reducing these cross products to the essential ones that will do the job for you in a predistortor and give you a relatively small number of coefficients that you can manageably calculate in a reasonable time. A technique that I've used, dynamic deviation reduction, which was developed by Professor Ending and Joe about 10 years ago now, and is being implemented in practical DPD systems. Why are these cross products important? Here's relatively simple structure. These are two wideband CDMA signals with a gap in the middle, so 15 megahertz, not tremendously difficult. You can see the intermod terms here and all the distortion products in the skirts here. And with a memory polynomial predistortor, you see you get reasonably good correction. I mean, this is actually pretty darn good. But you see some little skirts around here and here. Whereas using the Volterra series with dynamic deviation reduction, which is, as I say, is a technique for crossing out a lot of the cross terms, then for a similar number of coefficients, you're getting a much better, much cleaner signal out from here. Might not be terribly important in handsets, but if you've got a several hundred watt PA, this small bit of signal here defeats your spectral emission mask, which is an absolute value of minus 13 dBm or something like that. So you're really screwed if you can't get rid of these close-in things. And so this is what the Volterra series can help you do. And if you're clever about crossing out the cross terms that you don't need, then you end up with a system that's reasonably well put together. So we're talking about the coefficients in the DPD system. And again, I will hint about bandwidth in a few minutes. So the DPD has got to adjust the lookup table or polynomial coefficients as the signal changes. And things can change. This is another corollary of the wider bandwidth, and the signal traffic changes can change on almost a frame-by-frame basis every, say, millisecond or 10 milliseconds or whatever. The power levels can change. For multi-carrier GSM, the number of carriers and their location can change and all sorts of things. And so you need to adjust the parameters of your DPD to maintain convergence and minimize the distortion. Now, the beauty of something like a Volterra series or memory polynomial is that all the nonlinear parts are contained in a nonlinear function, the x squared or the x cubed or whatever, and the coefficients are linear. So if you write out this nonlinear, coefficient and nonlinear basis function sum of all the features that you have, then you can write that in what looks like a standard linear equation. All your nonlinearity is captured in this U matrix, and your coefficients are just linear coefficients of that matrix. And so you can end up, you can use standard least squares techniques to find the DPD parameters. And these are the ones that you adjust in the convergence. And so you actually are solving a very complicated nonlinear problem with least squares techniques. Least squares techniques have their own difficulties, and again, I've seen this over the years. Naive way of using this is, well, okay, why is this nonlinear matrix multiplied by the coefficients? I can just invert this matrix and get my answer. The problem is this isn't square, so this doesn't exist, which actually is a bit of a problem. You're going to end up with a whole bunch of things that don't happen, even though people try this. So really we need another approach. Okay, the usual least squares approach that you see in almost every paper on DPD is, you recast, let's go back, you recast this equation, multiply this by its Hermitian, then take the inverse and do the same on each side so that you end up with this equation, which is actually quite expensive. Although this now, because this is not square, because U is not square, you couldn't do a straightforward inverse, but this technique, this becomes a square matrix, so you can generate the inverse, which brings us to the next problem. Matrix inverses are quite complicated and expensive to calculate, so you'd really rather not do that. You're now multiplying two matrices together where the numbers, 11th degree polynomial has, can be a very large number, whereas linear term is relatively small, so you can have a very large range of values in this matrix. In other words, it's got a very large condition number, is what the mathematicians will say, or it means it's very difficult to multiply that 10, 15 order of magnitude range of numbers together and get a sensible estimate of your coefficients. A whole range of things can be done. Regularization is a very common technique, which essentially is you reduce the values on the diagonals and modify the eigenvalues, essentially is what you're doing. This is known as Tikhonov regularization, or computer scientists call it ridge regression, and I've used this and it doesn't work very well. So you need a better solver. Singular value decomposition is extremely robust to ill conditioning. It works in a lot of very unfriendly conditions. And this is a math, but I don't need to go through all that. But essentially, it calculates a matrix here that is a diagonal matrix whose entries are the eigenvalues of that product of the original U matrix, which is one of the features you're trying to calculate. And so you can get the inverse of that matrix and plug that into. So this is now the inverse of your original U matrix, and now you can plug that into the original equation and obtain the coefficients. As I say, it's very robust. It's just that this is an enormously difficult calculation. It takes time. It's quite expensive. One I tend to use quite a lot is QR factorization. Assuming that the matrix U can be written in this form, where Q and R have these particular properties, you can estimate the parameters in this way, and it actually works out quite nicely. This is, again, extremely robust to ill conditioning, which you're likely to get with this wide range of values in the matrix U and with noise. And it's actually reasonably straightforward to implement in C code, so it's actually nice to implement on a system. So this is pretty nice to use. Just for information, if you're doing it all in MATLAB, the / operator is the QR factorization for non-square matrices U. So you get it automatically without thinking about it. So just to summarize, linear least squares estimation requires the matrix inversion, or use SVD and QR techniques for robustness, and that's fine. Least mean squares I've not seen that used much, but it does avoid the matrix inversion. I have used recursive least squares, which again solves the UHU matrix in an ongoing manner, so you don't have to do a block conversion. And I've used that; it's been quite successful, and it's fast. It converges a lot more quickly than these techniques. And so, if you want to try and get some convergence in a very short space of time because your traffic is changing, then this is potentially a way to do it. So, the DPD challenges that I've tried to elucidate have all focused on wide bandwidth. We've seen multi-band and multi-carrier and multi-protocol signals, very wide bandwidth. That requires much more DSP power and much higher sampling rates and clock frequencies. Not to mention possibly a much more difficult PA design to do too. Real-time DPD coefficient updates are something that is sort of a corollary to this because people are changing the signal values all the time. But out of the main challenge is actually making it all work, period. But making it all work with low power consumption and low cost so you can sell it is the real challenge. And so that brings me to the end of my 45 minutes. So if you've got any questions, I will be happy to attempt to answer them. The question was, how do the polynomial models that I presented relate to AM to AM and AM to PM curves? If you look at an AM to AM curve, essentially a compression curve, what essentially you're trying to do is generate a model of that curve. If it was an instantaneous AM to AM curve, I could fit that with an instantaneous polynomial of whatever order. So that's where the polynomial part comes from. If you actually take, say, a real-time spectrum analyzer or a vector signal analyzer, and you take your PA and you apply a modulated signal to it that spans the input AM to AM, if you like, the input power range, then you'll see a signal that is not just the compression line, but it'll be compressed and it'll just be a cloud of signals. And that cloud are the memory effects caused by, this is just on AM to AM. It's the memory effects caused by things that for a given input signal, you can have a variety of output levels depending upon what the previous n input signals happen to be. If they're all very high and your PA was running hot, then for a given input level, your gain would be low, so your output would be lower. And so the actual output depends on the history of the input signal, not just the instantaneous value. So the straight line is just an instantaneous signal. The cloud gives you the history, the statistical history over all the signals that you happen to put in at that time. And it's that cloud that you're trying to model with these memory polynomial and Volterra series with the delayed versions of the signal as well. And you need to do that in order to get the correction that you need. If you just used an instantaneous correction, instantaneous model for DPD, you would get some correction, and sometimes it would be good enough. Perhaps for a handset PA, an instantaneous correction would be good enough to meet the spec. For most macro base stations, it doesn't get you anywhere near. You need to build in these memory effect terms to pull that distortion correction down to meet the spec. The question was, in the DPD system, which is a feedback system, as the bandwidths increase, how do you avoid instability? Yeah, instability is a well-known problem in feedback systems, especially as the bandwidth increase, and it is a problem. It's easy to say, let's have a gigahertz bandwidth, instantaneous bandwidth system, and see how well it works. In practice, you still have to put some filters around on the receive path to manage the bandwidth to something that prevents the instabilities. But they do occur. and it's a matter of tweaking as much as anything else to try and avoid them.
Can you say something about pruning the DDR coefficients? Is there a nice technique for doing that, or is it purely trial and error to see which coefficients you need?
There are a number of the context of pruning was, let's take a Volterra series, and given a polynomial degree and a number of and a memory depth, you can end up with 500, 600, 700 coefficients, and you need a way of managing those down to something that when you do the least squares analysis, you just don't end up with garbage at the end. So I would tend to say a figure of somewhere between 50 and 100 coefficients is reasonably manageable. So how do you get from 1,000 coefficients down to 100 coefficients in a sensible way? There are various techniques. The memory polynomial is a very good way of doing that, because it cuts out all of the cross terms so that every polynomial has the same delay. So there are no cross terms. So that's a very efficient way of getting rid of coefficients, but unfortunately doesn't give you the best correction for wideband systems. The dynamic deviation reduction is a sort of a step up from that in a sense, in that if you have a dynamic deviation reduction value of 1, it allows you to have one delay term that is not 0. So essentially you'd have an instantaneous polynomial and then t-1 delay, or t-2 delay, or t-. So that again has cut down the number of coefficients enormously. And you can increase the level of dynamics so that in any particular polynomial term you might have 2 non-zero delays or 3, but then the number of coefficients is going up all the time. But the dynamic deviation reduction has been quite successful. It reduces the number of coefficients quite a lot. Another technique is the generalized memory polynomial, which allows you to have, instead of in a memory polynomial all the terms are the same, it allows you to have one term that's different. So it's a sort of variation of the dynamic deviation reduction, whereas instead of them all being instantaneous except for 1, they could all be delay of 1 except for 1, and that would be delay of 1 or 2 or 0 perhaps. And so it's really just a way of getting rid of just, you might say, the random delays that the Volterra series permits, and they're systematic. They're systematic in a sense that they're easy to codify. It's easy to build an algorithm to generate a DDR set of values, or a generalized memory polynomial set of multiplicands, if you like. So that's reasonably straightforward. And that's really the only reason I suspect they're popular, is that they're easy to code. They may not be the most optimal set of coefficients. Yeah?
For the power amplifier design, there is this trend to use gallium nitride instead of the DMOS, right? And these gallium nitride devices, the transient behavior is very different to the DMOS, right?
Yeah.
Do you have any experience here how to take this into consideration in the DPD, or to explain
Well,
for the gallium devices?
Luckily, I have no direct experience of GAN PAs, so I can answer that truthfully. But the people that I speak to in the business, they have significantly more memory effects because the transients, you say the transient effects, knee walkout and all this sort of thing. And what it means, I believe, is that you end up having more, let's say, more memory terms for a given polynomial. One of the other ways of reducing coefficients is it's generally found that for the high degree polynomials, you don't need as many memory terms. So whereas for the third degree, the cubic, you might need 5, 6, 7 memory terms. Fifth, you might need 4 or 5. At the 11th and 13th, you probably don't need any at all. my understanding is that for gallium nitride you might need more memory terms at the higher orders because the curvature of the IV plane is more significant. Okay. Alrighty. Shameless self-promotion. There you go. Just came out last year. So I think I'm done. Thanks very much. Thanks for your attention.